Kinematics is the study of the motion of objects, omitting the forces acting upon them. Here are the kinematic equations that we will be dealing with. There are several other equations. These are just the basics, but for our purposes, they will do. To see these cute little equations in action, let us look at three different scenarios: a sprinter sprinting, a race car racing, and a book sliding. In our first case, we have a professional sprinter sprinting 100 meters. And he crosses the line faster than the eye can see. I say this with confidence because a pigeon and I were watching this from behind. And since pigeons, like all other birds, have very good eyesight, the bird was able to compute and identify and tell me that this runner took 0.4 seconds to run the first 5 meters. Therefore, his velocity in the first 0.4 seconds was 5 divided by 0.4, displacement divided by the time taken. And that would be equal to 12.5 meters per second. And since he was running at full pace, he would be accelerating. His velocity is changing. It's increasing as he's continuously trying to run faster and faster. His exact acceleration can be found using the first kinematic equation, Vf equals Vi plus At. His initial velocity when he began the race was 0 as he started from the starting line. His final velocity over the first 5 meters was 12.5 meters per second, and the time taken to cover those 5 meters was 0.4 seconds. His acceleration therefore would be equal to 31.25 meters per second squared. So, assuming that this was his constant acceleration throughout the remaining entirety of the race, we can calculate the time he took to sprint those 100 meters using the second kinematic equation. Plugging in the values that we have for the variables, we get that the time he took to complete the race was 2.5 seconds. Fastest man in the world, Usain Bolt, took 9.6 seconds to cover 100 meters. Yeah, you call yourself Bolt? You're a sloth. I think it's time for the trophy ceremony. Thank you. Thank you. Thank you. Wait. In our second case, a race car is... Wait. Why, no, not that one. Yeah, that's better. Wait, no, it still doesn't look good, right? Yeah, now we're talking. The starter raises his flag high into the air and swings it down, and off the line the driver floors it, accelerating like crazy. Oh my god, this is awesome. The beautiful drifts and turns and across the line. This car completed 6,000 meters of tarmac in 1 minute and 20 seconds. I guess there really only is one question now. How fast was it going? Well, plugging in what we know into the relevant kinematic equation, we get that it was traveling at a speed of 150 meters per second, which is about 540 kilometers per hour. Notice that this is merely the average velocity, not the velocity of the car at every moment of the race. Some people will tell you that the Bugatti Veyron or any other supercar is the fastest out there. But tell them that you know that that title belongs to this baby. Now, I don't mean to burst your bubble, but these equations cannot really be used to model the real motion of a moving car or a person. This is because they can only be used in a situation of uniform acceleration. This means that they can only be used when acceleration is constant, or if on an acceleration time graph you get a straight line. But in our situation, we do not get a straight line. Take, for example, the sprinter. We had idealized the situation by saying that the sprinter was constantly accelerating by 31.25 meters per second squared. But that does not happen in real life. Think about it. When you are running, you at first are increasing your speed like crazy, and then your acceleration decreases and eventually flattens out as your speed steadies. And for a situation like that, the acceleration time graph looks more like this. So, here is a scenario that does have constant acceleration. In this final scenario, you see the book is skidding along the table before it eventually comes to a stop. Its final velocity, therefore, is 0 because at the end it stopped. It doesn't have any velocity. Let us say that the initial velocity was 1 meter per second. So when you pushed the book away from you, it was traveling with 1 meter per second before slowing down. The displacement of the book is 1 meter, and so the final position is 1, and the initial position is 0. Throughout the sliding, the velocity of the book was changing, it was decreasing. Right at the beginning, it was traveling quite fast at 1 meter per second, but immediately it began to slow down, and within 1 meter, it came to a total standstill. Therefore, there was some acceleration here because its velocity was changing. What was that acceleration exactly? Well, we have everything we need to calculate just that using this kinematic equation. To minus 1/2 meters per second squared. So, as we can see, the acceleration was negative, whereas our velocity was positive. This means they were both in opposite directions. And as we saw earlier, when acceleration is in the opposite direction of velocity, the object is slowing down. But why did this book decelerate in the first place when you pushed it away from you? Was there some tiny driver inside slamming on the brakes? Well, surprisingly, no. The answer lies in, as is the case with most things in life, forces. Hi, thank you for watching this video. If you feel certain explanations weren't understandable or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I have also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.